All right, let's take a deeper look at section 5.2. In the order that I was going to conduct the lecture, I'll be going through these slides, notating them, and then posting them for your review and hopefully your understanding. Starting at the first page of the section, we have this diagram that talks about relative minima and maxima. The terms minima and maxima are plural. Minima is plural for minimum, while maxima is plural for maximum. Both of these have a generic group term called extrema, which is plural of extremum. So if I use that vocabulary, if I use relative extrema, that means I'm talking about all relative minimums or maximums. If I talk about relative extremum, I'm referring to one specific minimum or maximum. This diagram pretty much shows the difference, although it doesn't use the vocabulary that I'm about to show you, is that in just this example, let's talk about this relative minimum right here. We see that this point is the lowest point in that neighborhood. We also see that, and as the textbook vocabulary shows, they call it the deepest valley. So we're going to assume, based on the diagram, that that is the lowest point overall, which means its y-coordinate has the smallest value. What's interesting, or a question for you, is this point here also a relative min? I'll let you pause and think about that. Is this point a relative min? The answer is yes. It is obviously the lowest point in the neighborhood. However, it has an additional distinction, being, according to the vocabulary shown there and the diagram, the lowest point overall. That makes it in addition to being a relative min, it is a global min. Please make sure you have the vocabulary tattooed on your brain. As a reminder, you can have the word local used instead of relative, and you can have the word absolute used in place of global. One is not more correct than the other. There's no reason to use one over the other than preference, of course. All right, back to the diagram. We also see that there is a relative maximum right here, and this highest point is not only a relative maximum, it is a global or absolute, maximum. All right, not much happening here except the reminder that an absolute extremum is also a relative extremum. And the vocabulary, and we're on to the next slide. All right, let's read this one together. A function f is said to have a relative maximum at x sub 0 if there is an open interval containing x sub 0 on which f of x sub 0, which means the corresponding y-coordinate for x sub 0, is the largest value. That is, f of x sub 0, also known as y sub 0, is greater than or equal to f of x for all x in the interval. Similarly, blah, 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 relative min, blah, blah, blah. The question that always comes up with this definition is, what about a constant function? Do you have relative minimums or relative maximums, and don't you have a whole bunch of them, et cetera, questions like that. So if we consider f of x equals k, okay? I want to draw your attention to this phrase, at x sub 0. And I think it's also here, at x sub 0. X sub 0 is the location of the relative or absolute extremum. That's important for what I'm about to say next. The y coordinate, or f of x0, or y sub 0, or the function value is the extremum. Now we're going to pause together while you think about that. So, yeah, nice pause, I know. X sub 0 is the location of the relative extremum. The y-coordinate is the relative extremum. So in this case, up here, K is the local min, or sorry, the relative. Actually, you can call it the absolute also because it's a constant function. Absolute max is K. It occurs at all x values. So it's like, where does it occur? Everywhere. However, it has only one relative or absolute maximum, K. If it were like 4, the relative or absolute max would be 4. P.S., same with the min, because it's a constant function. Same for min. So the relative or absolute minimum is, let's say 4, whatever your K value is. Where does it happen? Everywhere. You have multiple x sub 0s, but you have only one y sub 0. So don't get drawn into the temptation to say, oh, look, there's an infinite number of relative extrema. No, there's one relative extremum. It just happens to occur at an infinite number of x values. Important distinction. Very good students throughout the years have gotten caught up in that way of thinking. Next slide. There's a lot going on this little slide. We'll sort of go back to some of the vocabulary we talked about at school today, and also remind ourselves that if a given statement is true and that statement is in conditional form, its converse is not necessarily true. So let's take a look at theorem 5.2.2. If a function f has any relative extrema, remember this is a conditional, we're not saying that it has relative extrema, but if it has them, then they occur at the points where the derivative is 0 or at the points where f is not differentiable. We know from today that these points, if they exist, are called stationary points. And these points, if they exist, are called points of non-differentiability. Together, these are critical points, which makes sense because something significant is happening on the function. Something critical is happening. So critical points come in two varieties: stationary points or non-differential points. Points of non-differentiability, excuse me. Again, I cannot say this strongly enough. If the extrema exist, then they occur at either those points. So in short, extrema occur at critical points. In short, extrema occur at critical points. All right, let's look at the very, 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 very not true converse. You could say it's, oh, well, maybe it's sometimes true. Look at this example, and sometimes it's not true. So the exact phrasing is that the converse is not logically equivalent. So since we want theorem 5.2.2 to be true, and it is, then we cannot assume that its converse is logically equivalent, meaning we cannot assume that the converse is true. The converse would be the converse of theorem 5.2. Whoops, too many points there. Would be, and I'm saying it would be because it doesn't really exist. There's no converse of this theorem. But it would be something like if f of x sub 0 equals 0, or f prime, x sub 0 is not defined, then there are relative extrema at all, whoops, I got a little happy with the T, extrema at all x sub 0. Good. Take a good long look at that. Enjoy reading it. And now let's scratch it out. Can I overstate that anymore? Is it possible for me to overstate that? This is not true. If you would like a 0 on your next test question dealing with locating the extrema, please assume that it is true. You have my blessing, with the warning that you will lose all points, no partial credit for such a rookie mistake. It is not true. Please do not think that it is true. This graphic over here is nice. Stationary points right here, SP, right here. And then I'm not even going to try to abbreviate points of non-differentiability. What would we call them? Pawns? Pawns with a D? And it's just more confusing. In any case, those are points of non-differentiability. There's another stationary point. The one important takeaway for points of non-differentiability is that they exist in the domain. So note the x, maybe I should say x values of, after I said I wasn't going to abbreviate it, now I have to abbreviate it. PONDs, which is weird because non-differentiability is one word. I don't know why I'm using an N and a D. Because pond looks funny. Are in the domain of f of x. You have to double check that they're in the domain. Oftentimes, the derivative winds up being undefined, like on a vertical asymptote, where a function would be undefined. So it makes sense. You can't get lulled into thinking, oh, just because the derivative's not defined, that must be a point of non-differentiability. No. You have to double check that where the derivative is undefined is on the function. If it is, then it's a point of non-differentiability. If it's not, then it's just a point. Next slide. Yeah, I can sum this one up in like 30 seconds. We've already done it before. The first derivative test, the first derivative test is the formal name given to the process of verifying extremeness by looking at the sign change of f prime of x. I'll pause for dramatic effect. Okay, I'm back. Nowhere is it said that f prime of x equaling 0 somehow guarantees extremeness. You have to look for the sign change. You want to look for the zeros? Go ahead. 0 will also be the number of points you get. You have to look at the sign change. And again, looking at the sign change or the sign change itself, the boundary between a plus or minus plus on the derivative sign chart can be at a critical point. That is a stationary point like that. Whoops, that's a weird looking dash. So, hey, x sub 0 is a max. Or it can also be, like, let's say it's not defined and it looks like that. Hey, x sub 0 is a max, provided it's in the domain. That's it. That rewarns us that just because the derivative is not defined does not mean that you have a point of non-differentiability. You have to check and see if it's actually on the function. Next slide. I can probably get away just by looking at this and having you look at it and narrate it a bit because we've already discussed it in class. The second derivative test is the formal name, given to investigating the first and second derivative together. You have to look at the first and second derivative together. Notice that both first and second derivatives have to be defined in order for you to look at them together. If either f prime of x or f double prime of x is undefined at x sub 0 and x sub 0 is in the domain, go back to the first derivative test. The first derivative test is a little more robust. That's actually a real word. It's not a Toryism, meaning it stands up to undefined function outputs for critical points. The first and second derivative, both having to be defined, and the first derivative having to equal 0 kind of limits you to just stationary points and an existing second derivative. So it pretty much occurs in happy land, which would be polynomial functions, trigonometric functions, of course, and anything else that's happy. So these are all like, well, yeah, it's obvious. Even look at the diagram. It looks like a polynomial. So the second derivative test is really kind of wimpy. It doesn't do much because the function has to be defined, second derivative has to be defined there. The function not only has to be defined, it has to be locally linear. We're really talking polynomials. So second derivative works, second derivative test, works. It's just only works for well-behaved functions. And rest assured, we are moving into, what are we going to call them? Ill-behaved functions. Works for me. Using the second derivative test does have a second caveat, and that's this inconclusive conclusion. So here, if you get a 0 for both first and second derivative, your test is inconclusive. It's like the test version of indeterminate. Don't make a guess. Don't do anything. You're like, I can't do anything. So this caveat also applies to the inconclusive case for the second derivative test. So if you get an undefined first or second derivative, and the point you're looking at is in the domain, of course, then you can go back to the first derivative test. It'll handle that. If you get an inconclusive result from the second derivative test, go back to the first derivative test because it'll handle that. Next slide. All right, let's pick one of the problems from the problem set. I am looking at page 3. Whoops, I don't want to write in that color. Excuse me. Page 304, which is section 5.2, number, stay away from happy ones, 27. F of x equals x to the 4/5. F prime of x equals 4/5 x to the negative 1/5. Instructions: use any method to find the relative extrema of the function f. I'm going to stick with the first derivative test. I don't know about the second derivative test. If you want to try it, try it. X, f prime of x. So this value that I'm going to put here has to be a critical point. Okay, looking at f prime of x, I can say erroneously that, oh no, there are no critical points because the first derivative equals 0 nowhere. Way false. Way false. f prime of x equals, and I'm going to change its format a little bit, 4 over 5x to the 1/5. Property of negative exponents. Check with an Algebra 1 textbook if you didn't follow what I just did. You would be wrong to say there are no critical points because f prime of x equals 0 nowhere. You would be wrong. True that f prime of x doesn't equal 0 anywhere. If you set it equal to 0 and try to solve it, it's not going to work. However, f prime of x is undefined at x equals 0, double checking, like we had said, oh yeah, and x equaling 0 is in domain, so x equals 0 is a critical point, which means it gets to be on our sign chart. X value is 0, the derivative is not defined. So your sign chart looks like that. It's fine. Now let's pick values on either side of the critical point, -1 and 1. You can pick any positive values you want on the right, negative values on the left. I'm picking 1 and -1. So check now. F prime of 1 equals 4/5, 1 to the -1/5. Looks like that comes out positive. F double prime of -1 equals 4/5, -1 to the -1/5. That comes out negative. So I have negative on the left, positive on the right, and we know from reading the sign charts last week that you have a minimum or a maximum because the signs change. So got it. Hey, notice sign change. Hey, from here to here. Hey, notice sign change. Okay, now you have to find out what was the transition. Well, f prime describes tone. Therefore, the function is decreasing, and then it stops decreasing, and it goes to increasing. Therefore, x equals 0 is a relative min. Do not ask me if it's a global min. We will do that in Chapter 6. All right, let's see if I can pick out another more challenging one. Next slide. All right, let's look at one focusing just on the critical points and what type of critical points they are. I'm looking at whoops, again, sorry about the color. I'm looking at page 304, which is section 5.2, number 11A. And 11A says, excuse me while I scroll, in exercise 7 and 12, locate the critical points and classify them as stationary points or points of non-differentiability. So the function we're dealing with is in A, x to the 1/3, quantity x plus 4. Looks like I need I need another parentheses. I need the first derivative. I don't need the second derivative. I'm not doing anything with it. So I'm looking at that, and I have to use the product rule. No. Let's do something else. X to the 4/3 plus 4x to the 1/3. You have to deal with a little fractional exponents, but I can deal with the exponent rule twice rather than the product rule. So a little manipulation there. Let me double check my work. Life looks good. All right, first derivative. 4/3 x to the 1/3 plus, why does this look familiar? Is this one we did in class? 4/3 x to the -2/3. It is. All right, so I'm going to look at that. First step, stationary points. Actually, I'm going to back that up. I'm going to look for points of non-differentiability first. Pawns, that still cracks me up. Look at where f prime of x is not defined. I'm sure we can do that by inspection. Let me pause for dramatic effect. X equals 0. X equals 0 is a pond. Two reasons make it so. First of all, 0 with a negative exponent is going to give you a term that's undefined. And secondly, please tell me you double check that even before I said to. 0's in the domain, so it's a pond. Otherwise, it would be just a point. It would be just a P. All right, now let's look for stationary points. Again, we're going to set this thing equal to 0, and we'll do a rehash of what we did in class. So 4/3 x to the 1/3 plus 4/3 x to the negative 2/3 equals 0. You could try to do some factoring with that, but I'm going to do it the way I did it in class. Forgive me. Multiply through by 3/4 x to the 1/3 plus x to the negative 2/3 equals 0. X to the 1/3 equals negative x to the negative 2/3. That's a weird looking 2. Sorry about that. X to the 1/3 over 1 equals negative 1 over x to the 2/3. You might have another way to do it. I'm maintaining this is my way. X equals, it's x to the first, right? Equals negative 1. And we're pretty much done with that. Let me double check that. That's fine. And we didn't have to like look for extrema or anything else. We just had to determine the critical points and the classification. So pardon me while I double check my work on the solutions. 11a. X equals negative 1, stationary point. Does not exist. X equals 0, point of non-differentiability. Works for me. One more slide, and then I'll post these. Next slide. All right, I'm looking at section 5.2, page 304, number 13. Use the graph of f prime shown in the figure to estimate all values of x at which f has a relative min, a relative max, and an inflection point. All right. If I look right here, x equals 0 is a stationary point. Please tell me you know that. X equals 2 is a stationary point. Okay, looks like, and I'm not exactly sure how you want to do this, so bear with me. If I do a quick sign chart, do a quick and ugly sign chart, x, f prime of x, boom, 0, plus, minus 0. To me, that looks like x equals 0 is a local max. Now, I want you to notice something. If I were to take this sign chart right here and magically superimpose it on the graph, and it would look like this, sort of, right? And we're looking at the derivative output, right? This output, trying to write sideways, excuse me, be 0 here, negative here, and positive there. So we're really looking at just a graphical sign chart. You're taking the sign chart and you're superimposing it on the graph so that the output signs, which is why I said to notate your sign charts that way, correspond to the graphical position of f prime. It's no harder than that. So similarly, if I look at this one, x, what would that be? X equals 2, f prime output, 0, to the left of 2 it's negative, to the right of 2 it's positive. And if I go over and I superimpose it right here, I get 0, negative, plus. And it looks like, hey, x equals 2 is a minimum. So x equals 2 is a minimum. And I forgot to conclude what we did on the other one. X equals 0 is a max. All right, and the last thing is to look for inflection points. I am not sure where we left off in how many different connections we wrote regarding what does it mean on F prime, what does it mean on F and F double prime, etc. We are looking for F inflection points. So what I want is I want the concavity change points of f of x. That means I want to know where the second derivative of f changes from negative to positive or positive to negative. Interestingly enough, the tone of f prime is the concavity of f. Again, I'm going to pause for dramatic effect. Okay, so where the concavity changes on f, which would be our inflection points, is where the tone changes on f prime. Well, we know that tone changes at extrema. So all told, extrema on f prime correspond to points of inflection of f, which, just for the mathematically curious, correspond, to x-intercepts of f double prime. All right, so looking at that, I'm going to estimate that x equals 1 is a point of inflection, and x equals 3, point of inflection, both of these on f of x. All right, looks like we're done. I'll post these, and you can view them over and over and over again. How fun is that? Should I pause for dramatic effect?